So today we're discussing vehicle motion along a circular path. So we'll be focusing on the maximum safe speed. What are the conditions for us to achieve that? So to start, we have this situation. So you may be given a number of conditions for you to achieve the maximum safe speed. It could be that the vehicle may skid outwards, or it may overturn, or that the road surface that is being used is already banked. Now, what happens if you are in a vehicle which exceeds the maximum safe speed, or maybe it is carrying a load such that the center of gravity is far higher from the ground? Just take a look at this short video clip. It will illustrate what we're trying to discuss here. Now you see this truck already in motion. It turns there and already it overturns because it's no longer able to contain the factors that should keep it stable. The speed at which the tracker was running, it might have been trying to mimic this other vehicle behind it, trying to move at the same speed with this one. But this is a lighter vehicle and this center of gravity is far closer to the ground. So it caused that truck just like that. So what should have happened? If he had slowed down, that risk wouldn't have come about. So these are some of the factors that lead to accidents, but rest assured, during design, they are well taken care of. So this is what we're talking about. The condition in that clip is about overturning. What may cause that? And you notice that the most important factor is, or rather one of the most important factors, is the height of the center of gravity above the ground, like this vehicle. How high is the center of gravity from the ground there? That is one of the factors that becomes very important. And also, what is the coefficient of friction between the road wheels and the surface? Many more of those. So here's a typical example. You have this car which is negotiating this corner. We're discussing skidding speed on a level track. If the track is level, then what? So it is negotiating this curve. This curve also has a radius, meaning from this vehicle where it is up to the center of this circle, or being a circular path as it is. So two main forces are at play. The one that is acting on the road wheels there, pulling it towards the center so that it does not spin away, is the friction force. Then the one which is trying to push it away from its rotation, from its path, so that it can overturn or skid outwards, or rather it may start by skidding, or later on maybe it may overturn. It's this force here, the centrifugal force, given by mv squared over r. If these forces are in balance, and especially if this is far higher than this one, then this can safely negotiate the curve. So a vehicle is at the point of skidding when these are just equal to each other, as you can see there. So then you have the centrifugal force being equal to the friction force. So if you look at this expression, you just make V the subject, that's what you have. Things will cancel out, then you end up with V is equal to the square root of coefficient of friction, acceleration due to gravity, and the radius of the path. That is for the condition of skidding. However, like we said, the center of gravity is very critical in this case, because if it's very high above the ground, going up there, then even its tendency to overturn is high, like we saw in the track in the video. So if it's lower, closer to the ground or flat, then even the speed at which it can negotiate such a curve is also improved. So the two forces at play are the centrifugal force and the weight. And they create moments about this outer wing. So that if it has to overturn, then this will be the turning point, then tipping over of the inner wheel, and then see things happening just like that. So it means that I'll take moments about the outer wheel. The centrifugal force multiplied by this perpendicular distance. The perpendicular distance is the height from there coming there. That is h. Then the perpendicular distance for this, which is the weight, is the distance from here coming all the way to there. The distance between the track, or rather the two wheels, it could be in front or at the back, which we call the track width, is given by the letter D. So because this center of gravity is at the center, so this D should be divided by 2. That's why we have mg multiplied by that track width divided by 2. So that's how come you have that as your anti-clockwise moment. The other one, which is a clockwise moment, is centrifugal force times the height of the center of gravity above the ground. So we have mv squared divided by r multiplied by this height. There we are. If you notice on both sides, you'll notice that the mass is common. So this mass can cancel out. Then you have v squared over r times h being equal to g multiplied by d over 2. Now from this, you can just make v the subject, and that's what you're going to have. grd over 2h. H representing the height of the center of gravity above the ground, r the radius of the curve, meaning the radius of the road surface from the center. Like it is, that radius is where this vehicle is up to the center of the circular path along which this vehicle is moving. Then we also have D, like we said, that's the track width, meaning the distance between the two wheels in front or at the back. Then that gives us a complete formula right there. But there's another condition that improves on the speed at which a vehicle can go around a curve here. This is known as banking. What may happen to cause overturning? Well, one thing you realize is that when a vehicle is about to overturn, there is that condition whereby the reaction on the outer wheel is almost zeroed. So here, if you were to look at these forces and make up a triangle, or rather a force triangle, this is the shorter version, because we're talking about that angle being very critical. That's the one of that theta there. So in this case, you'll notice that tan theta is v squared over gr, meaning the banking angle is given by the square of the velocity at which it's moving divided by that. Similar to the expression we had developed in a conical pendulum, because the principles are basically the same. So then, making v the subject, you have gr tan theta being equal to v. Now this having been done, you also notice we cannot just leave it here. Let's look at some examples that may illustrate what we are referring to in this case. So we have a motor vehicle which is required to negotiate a curve of radius 55 meters. And we are told the coefficient of friction between the road surface and the wheels is 0.6. Determine the maximum safe speed this vehicle can go around the bend without skidding outwards. So look at the information given. The radius of the road surface is 55 meters. The coefficient of friction between the road surface and the wheels is 0.6. Acceleration due to gravity is at 9.81 meters per second squared. Looking at this information, the condition we're using, we've already been told it's skidding outwards. And the expression we derived or arrived at was V being equal to the square root of mu gr, coefficient of friction times acceleration due to gravity times the radius. Now, what follows next you just substitute. The coefficient of friction is 0.6. Acceleration due to gravity is standard, 9.81. That's the one we're using. Then the radius of the road surface, 55. So this, when entered into your calculator, that's the end result. You have 17.992 in meters per second. Now, to illustrate this, you may find that the velocity that we found, we're not saying that it will be skidding. It is at the point of skidding. Should you exceed this one, then your vehicle will skid outwards. And of course, we know what happens after skidding. You see some overturning moment being created, or the driver losing control and other things. So it means that during recommendations, this is the maximum safe speed the vehicle may skid at any point. So recommendations may be just saying someone should not go beyond this velocity here. And we might as well convert this to kilometers per hour by just multiplying this number by 3.6, or multiplied by 3,000 divided by 1,000. 3,600 divided by 1,000. Then we get its equivalent in kilometers per hour. Now we can take it a bit further. Let's look at the next example. Here we have a motor vehicle which has a track width of 1.2 meters. Then the height of its center of gravity above the ground is 420 millimeters. So determine the maximum sail speed in kilometers per hour. This vehicle can negotiate a curve of radius 40 meters without overturning. So going back to the information provided, first we have the track width, which is represented by the letter D, 1.2 meters. The height or between the road surface and the center of gravity is 420 millimeters. Converting it to meters will mean we divide this by 1,000, then we have this, which is 0.42 meters. Then the radius of the curve is 40 meters. This is the information that has come forward. Then what do we need to find? We want to find at what velocity is it supposed to run. And then we convert it to kilometers per hour so that it can be understood by other road users or by others. So going back to the formula that we're supposed to use, overturning, if you go back to our analysis here, taking moments about here, this overturning moment and the righting moment are just supposed to be equal when we're at the point of overturning. So to get the maximum sail speed, that's how come we took moments about this outer wheel. Then this correcting or restoring moment, which is mg times d over 2, is supposed to be equal to this multiplied by that. And that is the formula we have there, which is v being equal to the square root of GRD divided by 2h. And let's see what is there. So having said that, we can now just do the replacement of these values. G is 9.81. R, we've been given, is 40 meters. D, it is 1.2 meters. 2 is there. Height of the center of gravity above the ground, or the distance between the road surface and the center of gravity, it's 0.42 meters. So then you have all the factors there. Then, since we've already made V the subject, we can just calculate this now and try to simplify all those. So when this is calculated, the end result is 23.676. It's in meters per second. But converting it requires that we take it from these meters per second to kilometers per hour. We need to multiply by 3,600 and we divide by 1,000. Why are we doing that? We want to convert this 1,000, this meters to kilometers. So that's why we're dividing by 1,000. The second, which is below here, we divide it by 3,600. We convert it from seconds to hours. So in the end, this whole number multiplied by this will give us the answer in kilometers per hour. And the final result is 85.235 kilometers per hour. In other words, a motorist negotiating this curve whose radius is 40 meters with a vehicle which has a center of gravity with a height of 0.42 meters with that kind of track width, he is not supposed to exceed that velocity. So if we have to tamper with this, increase on this speed, then we have two options. It's either we reduce this, meaning we reduce the height of the center of gravity, let it come down, or we increase this, which is a track width. But of course, these are factors that are designed at design stage. That's where these can be done. Or if you're on the panel making decisions about the size of the road, then you may increase this one, meaning you increase the radius of your curve, then you're also going to end up increasing the speed at which those vehicles can negotiate that curve. Whoever exceeds this speed with such a vehicle will end up going through that problem of overturning, similar to what we saw in that truck which was negotiating a curve and then at the same speed with another car which was following it, but it overturned because its center of gravity was high above the ground and it exceeded the speed which is allowed for it in those parameters. So that is how this is done. You can enjoy this by going through the exercise. This exercise, together with the soft copy, is posted on my blog. You can feel free to download it there. You can also read other posts which I've done there. And like I've always said, we have many more lessons coming, which may be posted from time to time. So feel free to subscribe and enjoy most of these lessons at your own free time. Thank you for watching and for following through.